Cool, so this is the Level 2 2018 Electricity exam. So for question 1, they say that they have a generator of two metal plates that are 0.08 meters apart. This is the distance. They give you the electric field strength. Is established between when the thing is turned on. Calculate the voltage between the two plates. So we have the electric field strength and we have the distance and we need to find the voltage. So looking at the formula sheet, the very first equation, which has all three of these variables, is E equals voltage over distance. So if we rearrange this to find voltage, we'll get voltage equals E times D. And then simply doing 2.5 times 10 to the power of 6 times 0.08, which is the distance. Yep, this should give you the voltage, which is 200,000 volts. Cool. So for the next question, a flame of a candle contains both positive and negative charges. Draw the electric field formed between these two parallel plates, metal plates. Okay. Well, so from this we know that the negative charges in the candle move to the left and the positive charges move to the right. A simple rule for this that you should probably know is that opposite charges attract and like charges repel. So from this we can see that the negative is being attracted towards the left hand side. From this rule we know that opposite charges attract, so therefore this left hand side plate must be the opposite of this negative charge, so it should be a positive, and vice versa, because the positive charges are being attracted to the right hand side plate, therefore it must be the opposite, which is negative. And in order to draw the electric field, this is pretty simple. So the electric field flows from positive to negative. To get the full marks, just make them nice and straight, evenly spaced. Should probably do this with the ruler. And the edges, just give them a bit of a curve. And yeah, so if it's evenly spaced and straight, that should be pretty good. Okay, so a stationary negatively charged smoke particle. This is the charge, is positioned centrally at position A, which is here. The smoke particle is accelerated to the left, so it goes this way as shown. And this is the electric field, which they also give. So the question says using conservation of energy. What that means is that the potential energy is exactly the same as the kinetic energy. There is no loss of energy. Calculate the speed of the, and they give you the mass as well. Smoke particle the instant before it collides with the left hand plate. That is distance. Okay, cool. So we don't need this distance because this distance is from the right hand plate to the left hand plate. We only need the distance from A to B, which is this. So firstly, when it starts at A, so let me just change the color real quick. So at A, the particle has potential energy, which is given in the formula sheet as EQD. So simply putting in the numbers that are given to us, so 2.5 times 10 to the power of 6 times 6.52 times 10 to the power of negative 13 times the distance from A to B, which is this 0.04. This gives us potential of 6.52 times 10 to the power of negative 8. So because of conservation of energy, we know that the potential energy will be exactly the same as the kinetic energy. So as the formula for kinetic energy is half mv squared, and we're looking for the velocity, the speed, we can simply rearrange that to voltage equals EK, and you substitute the half m and the thing. Yep, that is correct. So simply putting in the numbers again, so EK is exactly the same as EP, 6.52 times 10 to the power of negative 8 over half times the mass of 4.5 times 10 to the power of negative 6, all that. Square root equals velocity, therefore velocity equals 0.1723 meters per second. We shouldn't put it right there in 2 decimal points. 0.7 meters per second. 2 decimal p. Cool. So D. A strong permanent magnet is then placed high above the smoke trail. The North Pole is going to state the two changes not involving the magnet that can make the increase in velocity and the negative charge particle. This could be many different things, so we only need 2. So for example, because it's asking for a change in velocity, and we just did the formula before, velocity equals EK over half mass. From this we can see that if we decrease the mass, it will result in a higher velocity, or if we increase the energy, it will be a higher velocity. Also, energy potential equals EQD. So from this, we can also say that if we increase the electric field, it will result in a high velocity. Increasing the charge will increase in high velocity, also increasing the distance of the plate from A to B will result in a high velocity. Or if you want to go to a completely different route, you could say because E equals V over D, increasing the voltage will result in a higher electric field, and this will result in a higher force actually, and because force equals MA, the mass stays the same, the acceleration goes up, and as acceleration equals v over t, the velocity will increase. Sorry for the mess, but there are a lot of different ways you can approach this question, as we can see. So for one of the changes, explain. Okay. Let's pick mass. So if the mass goes down, the force stays the same. So as F equals m, a increases and therefore velocity also increases. Or you could say increasing the voltage. This will result in a higher electric field, and therefore the kinetic energy will go up. As a result, the voltage will go up. So this is simply decreasing the mass causes a force of the same magnitude to accelerate the particle by a greater proportion. So because F equals ma, you can simply say that force equals acceleration. If acceleration increases, the velocity must increase because that same particle has to move the same distance in the same amount of time. So next question is discuss what could be done with the magnet to affect the motion of the negatively charged smoke particle. There was only one right answer here, and that is to make the magnet perpendicular, which just means making 90 degrees to the motion of the moving charges of smoke particles. To the smoke particles. And this is because if it's perpendicular, the overall E will go up, as seen, because these will add to the electric field already on the plates. And well, yeah, so the force equals EQ, force equals MA, the particles will accelerate because of A. As the force goes up, the mass stays the same. So in order for the magnet to have the most effect on the motion of the smoke particles, the magnet must be placed perpendicular. It must be placed 90 degrees to the motion of the smoke particles. That is how you answer the question. And now the ammeter. So current passes the coil ABCDE with magnetic field. A current of 2.5 amps passes anticlockwise through the ammeter. State the direction of the force. Cool, so we can go ahead and label the electric field, which goes from north to south, so B the 4, and this be spinning this way. Thus the forces okay, state the direction of the force, if any, on each sectional wire. A to B, so we can see from A to B, the direction of the force is downwards. So this is the direction of the force here. B to C, there is no force. And from D to E, the direction is upwards. Cool. So for the next question, a total force of 0.6 newtons is produced on the wire within the amp meter when 2.5 amps is passed through its coil. Calculate the effective length of the coil around the points A to B. So, and they also give you the magnetic field strength, which is B on the formula sheet. So they give you the force, the current, B, and you need to find L. So the formula on the formula sheet that has all those variables is only one, which is force equals B I L. And rearranging that to find the length, L equals force over BI. And simply plugging in the numbers, 0.6 divided by 0.2 times 2.5, this gives us 1.2 meters. Now we have a length, but this is not the effective length of the coiled wire between points A and B. See what happens if this is your coil, and this is point A here, this is point B here. What we calculated is the length of this. What we need to calculate is the length from here to here, which is exactly half of this. Therefore, half of 1.2 meters equals 0.6 meters, which is the length from A to B. Sweet. Middle rod is moved downwards between the poles, and they give you the speed, the magnetic field strength, the size of the length of the rod. 0.6 is the width of the magnetic field magnets. Calculate the voltage induced. Okay. So voltage, looking at a formula sheet, the only formula that has B, V, and the length is voltage equals B, V, length. And simply plugging in the numbers, so 3.5 times 7.5 meters per second times the length of the magnetic field, which is 0.16, because the magnetic field is only acting this width, it's not acting for the entire rod, so we use 0.16, which gives us a voltage of 4.2 volts. And state which end is positive. Okay, so using the left hand rule, where your thumb is the motion of the rod, so thumb equals motion, your index finger equals the magnetic field direction, and your second finger equals the induced current, which is positive to negative always. So using the left hand rule, you can see that end A is positive. Cool. For experiment 2 and 3, state whether a voltage is induced in the wire AB. So yeah, so the rod and the wire are both inside the field. So yes. Nice and simple. Cool, so for this question, for each of the experiments, justify where the current flows through the closed loop. So for the first experiment, the wire is firstly not in the magnetic field, so that it has no induced voltage. The rod is moving inside the magnetic field, and because of V equals BVL, there will be induced voltage in the rod, and due to this potential difference, current flows. For experiment 2, both the wire and the rod are in the magnetic field, and we know that the velocity is exactly the same speed, so they will be moving at the same speed, and they are both in the magnetic field. This means the same induced voltage, and due to no potential difference, there is no current. For experiment 3, both the wire and the rod are inside. The wire, however, is not moving, so there is no induced voltage, and due to V equals BVL, the rod has a velocity, so therefore there is a induced voltage, and thus current flows. Okay, question 3. Use the following circuit diagram to answer the questions below. Show that the total resistance of the above circuit is approximately 10 ohms. Sure. So we see that bulb 1 is in series with bulb 2 and 3, which are in parallel. So an easy way to calculate parallel circuits is R1 times R2 over R1 plus R2. So basically this would be RT equals 4.8 times 7 over 4.8 plus 7. R equals 2.84 ohms. And circuits in series just add, so series, I'll just write it here again. So series R1 plus R2. Therefore, RT of the circuit equals 7, which is in series with bulb 2 and 3, which we calculated to be 2.84. RT equals 9.847 ohms. Okay. Calculate the voltage across bulb 1 and bulb 2. So for parallel circuits, the current is shared, and in series circuits, the voltage is shared. So we are calculating the voltage, so we firstly need the current in the entire circuit because Ohm's law states that V equals IR. Rearranging that, IT equals 12 over the total resistance, which is 9. I'm just going to round that up to A5. This gives us 1.22 total current flowing through. So for bulb 1, voltage equals the current. To understand, the current is flowing this way, flows from positive to negative. So it enters here, the full current will enter here, the total current. So it will be 1.22 times the resistance of the bulb, which is 7. This gives us an answer of 8.54 volts for bulb 2. Because in series the voltage is shared, the voltage that is lost here, or the voltage that is across here, is basically lost from the circuit because it's been used up by this resistance. So because voltage is shared in series, we can say that the total voltage minus the voltage across bulb 1 equals the voltage across bulb 2. Because the voltage gets used up here, it comes this way, and it's shared equally between both of these. So there's no extra calculations here because we know that the voltage, any voltage entering this junction of these two parallel bulbs, will be shared equally. So therefore 12 minus 8.54 voltage equals the voltage across bulb B, which is 3.46 volts. Bulb 2 and 3 are not the same brightness. Discuss which bulb is brighter and why. So we can see that bulb 2 and bulb 3 are in parallel, which we've discussed before. That means the current is shared in parallel. However, it is not shared equally. You see, current always takes the easiest path. Current favors low resistance. So as V equals I current equals V over R, we can see the bulb 2 has a low resistance of 4.8 compared to 7 ohms. More current flows to bulb 2 because of I equals V over R. Right? The smaller this is, the bigger this is. So because of this high current, the power consumed by bulb 1, and power is defined by I times V. For bulb 2, because this I is bigger compared to bulb 3, bulb 2 uses more power. So the brightness of a bulb is basically the amount of power it uses, right? So because there is a higher current flowing to bulb 2, it will use a higher power, therefore it will be brighter. And that's the answer. I'm sure you can do a better way explaining the question though. So an ideal ammeter with negligible resistance, so basically zero resistance, is added to the previous circuit as shown below. Discuss the effect of adding the ammeter has on the current, the voltage, and therefore the brightness, of course. So as I've said before, current takes the path with the least resistance. It takes the path with basically no resistance, the easiest path. Of least resistance. So the current flows to, let me do a better job here. So this is the current flowing to this junction. Here, this has a resistance of 7 ohms, and this has a resistance of negligible resistance, basically 0. So all the current will flow through the easiest path, which is through the ammeter, and therefore no current will flow through the bulb, basically shorting the bulb. So the bulb would no longer light up as there is no current flowing through here. All the current is flowing through the zero resistance amp meter. So this means that the total resistance drops by 7 ohms, or the resistance for bulb 1, because it is no longer working. So the current doesn't get resisted by the resistance that affects here, it goes through 0. So the total current will basically be these two in parallel in series with a 0 ohm resistance, which we can do here. RT equals 9.85 minus 7 gives us 2.8 volts total for the new circuit. And also as I equals V over R, because the overall resistance in the circuit has decreased, the new IT will be much larger. It'll be 4.2. So 4.2 amps will flow into this, the full 4.2, because this has 0 resistance. So in theory, no current is lost. So the full 4.2 amps will flow here into this junction of parallel bulbs. And because there is a higher current, there will be more power used by these two bulbs as discussed above. So as a result, bulb 2 and 3 will get brighter, and bulb 1 is effectively shorted, so bulb 1 will no longer light up.